Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Rob Farmer and Eva Laplace with us today. Hello, Rob. Hello, Eva.
Hi, Frank.
Hey. And let's start with you, Eva. Where are you located at?
I'm currently based in Germany, in Heidelberg. Lovely weather here. And it's the end of the day.
Well, I don't want to keep you too long from your German evening, so at least it's not Oktoberfest yet, so getting there.
Yeah.
And Rob, how about you? Where are you at?
So I'm also actually now in Germany. So I'm at the Max-Planck-Institut for Astrophysics in Garching near Munich.
Okay, very cool. And Eva, you're a grad student, postdoc there?
I'm a postdoc. I'm in the middle of my first postdoc at the Heidelberger Institut for Theoretical Studies.
Very cool. Very nice. And it is July 6th, 2023 as we record this, and it is definitely summer in Phoenix where I'm at. The heat button has been hit. We are going. Very cool. Let's see. And Rob, what do you like to do for research?
Yeah, so I do a lot of stuff with massive stars, binary, stellar evolution, help develop the MESA stellar evolution code.
Cool.
For you, Frank. And we also do a bit of supernovae work as well.
Very cool. And Eva, what do you like to do for research?
Well, actually pretty similar to Rob. We actually were in the same research group before. So I'm also very interested in knowing like what massive stars do for a living and also what they do when they die. And what's really cool is that it turns out most of them actually don't live alone, but have a companion. And that changes a lot of things. And I think we might talk about this today.
Very cool. Very cool. And that is going to bring us to this very awesome APJ article. It is open access. You can go get a copy for free, people. We're in the open access era. Go grab one. Nucleosynthesis of binary strip stars. And Rob and Eva, take us away.
Sure, thanks. So yeah, so this is a project that's kind of been many years in the making, kind of building off a lot of work that Eva was doing during her PhD. And we're basically, so that was with Selma Demink and Stephen Justin. And Jingzi Ma was actually a bachelor student with me and is now actually also at the Max Planck and doing his PhD. Cool. And we're really kind of trying to answer the question, kind of, what is the nucleosynthesis of a binary star? And, you know, how does that differ from if you're a single star?
Good.
Right? Can you treat, you know, a binary system as just two single stars, or is there something more complicated going on? Turns out it's, you know, a lot more complicated than, and you have to actually do some quite detailed modeling.
Indeed. Very cool.
So maybe Eva wants to talk about binaries.
Yeah, so this is actually really exciting because people have always tried to make these kind of predictions in the simplest way, and that is by treating all stars as if they were single. And so now that we have many more insights, thanks to observations of massive stars, we actually know that most of these massive stars have a companion star. And so we were really wondering if that plays a role. And especially because during my PhD, I looked at some of these stars that interact with their companion star and actually become what we call binary strip stars. So stars that lose their outer layers and give them to their companion stars. And it turned out so that not only the outer envelope of these stars is affected when there is a transfer of matter, but even their core structure can be changed. And that it turns out that matters a lot as well for the nucleosynthesis. Cool. And so the whole idea was to figure out like how these stars look like at the moment when they explode, and then to actually run these simulations of what kind of elements are produced throughout their life, but also at the moment of explosion. And we started doing this motivated by some of the work that I did, where we saw some hints that at least some of the lower elements would be already affected, especially carbon.
Okay.
And that led to our first paper.
Yeah. Mm-hmm. Very cool. Very cool.
Yeah.
And I think this is one of the first very detailed nucleosynthesis calculations of binary strip stars. Yeah.
Yeah, so we're using MESA models here of massive stars, so things above 10 solar masses, up to about 45 solar masses.
Mm-hmm.
And one of the big things actually for these models is that we're doing really detailed nucleosynthesis as we go. So we've got 162 isotopes in the nuclear network. That is slow to run. These things are order months to compute.
Yes.
So we're really, trying to be detailed with the nucleosynthesis and what that is doing inside the models.
Very cool.
So what we're doing is, we'll evolve, we only evolve one of the stars, and you can kind of just assume the second star is just a point mass. So it has some mass, but we don't care what its structure is doing.
Okay.
We evolve the system, and then as the stars evolve, they will get larger, they'll expand, and at some point they'll overflow the Roche lobe. So then material will then transfer to the companion, being taken off of what we call the donor, which was the initially most massive star.
Okay.
And then you can then follow the evolution through, take it all the way up to core collapse, and then we can then also do the explosion in MESA and look at kind of the nucleosynthesis coming out to that at the end.
Very cool.
Yeah, and we'll get to that at some point later, but we also have to decide whether this star is going to explode or not, because if it creates a black hole, for example, it might not contribute as much to enriching the environment as when it would actually explode. So we also have to decide about this in our computation.
Which would affect the yields. Yeah.
Exactly.
So yeah, so if you go to equation 1, so this is just, the definition of a yield. So just, how much material are you ejecting into the universe beyond what you started with?
Yes.
So the thing, you have to there's two kind of ways, the binaries could be different to single stars. The binary could intrinsically make something different, different composition inside, and that gets ejected. Or it could simply just change the amount of material you eject. So if you can eject more material, even if it's the same composition, then you get more yields out of a binary than a single star.
Well, I'm with you. Very good.
So yeah, so that was equation 1. So that's really kind of the things we've got to kind of think of is how does the amount of mass change and what does the composition change?
Okay. Very cool.
And then if you go to equation 2, we get to that question, which star actually explodes and which one doesn't. And there are several ways that people have identified to try to characterize this. One of them is called this compactness parameter that you see in equation 2. And then there are also other possibilities based, for example, on the entropy, where you can, like for the criterion from Ertl et al. 2016, like in equation 3, and the equation 4, where you have basically two parameters to figure out whether a star would explode or not. And we actually don't discriminate between them, but we use both to try to evaluate which one would explode or not.
Okay.
But we also know that for real supernovae, this would be more complicated, of course. This is an approximation for the sake of this work.
Sure. Like equation 2, the compactness parameter is basically GM over R. It's gravitational well.
Something like that, yeah.
Right? Yeah. Okay, very good. Okay, onwards.
Yeah, so I mean, we can quickly just look at equation 5. So it's a little complicated to think about, but really we're just making a definition at this point, which is kind of something about the fraction of material coming from one star, singles or binaries, and what mass loss process is it from the stellar winds, is it from the supernova, etc. And then it just gets kind of normalized by the total ejecta.
Total, right.
So it's perhaps a little clearer to see in the figure 1, which is kind of the plot of this data.
Let's take a look at figure 1. Fraction of IMF weighted. Okay.
So this is kind of the whole summary, I think, of the whole paper. Really, is kind of these plots. Is it's saying, you know, as a function of Z, so the proton number.
Okay.
So if you see the isotopes on the top, just map into the proton numbers.
Okay.
If you assumed you had a population of single stars and just the donor in the binary, so we basically ignore what the second star is doing.
Okay.
And if you assume these are, you know, about the same size, right, populations, what's the relative fraction of material coming from different processes?
Okay.
So we've got kind of working down from the top. So you've got the pre-supernova single star yields. So that's the stellar winds from single stars.
Yes.
And then in blue is the supernova from the single stars. Yellow/orange is the binary supernova. And then purple is the binary winds. But it could also be this material lost in the Roche-Lobe overflow as well.
Wow.
And then A and B, basically A is saying, so we have these 162 isotopes. Let's just say what everything is, you know, coming out.
Yes.
But a lot of these isotopes, you know, they don't live very long, right?
Yeah.
They're radioactive. They'll decay on short time scales. You know, you're not going to see their signatures. So what we're doing in B is saying, okay, let's take all these radioactive elements, work out where they go into, you know, stable elements, and then show that. So this is kind of, B is kind of what you might expect to see, say, in the galaxy over kind of a long period of time.
Yeah, and I think you can already see the main results of this paper summarized here. And that is basically the y-axis. So what fraction of the elements would be created in binaries versus single stars. And when we mean binaries here, we mean mainly the strip stars.
Okay.
And you can see that, like, even for both plots, you can clearly see that the binaries play a very, very huge role because they're main producers of most of the elements, apparently, based on our models. And you can see some really nice features as well. So, for example, what happens for low proton numbers and for high proton numbers, there's very clearly a difference. And there are some spikes that are also very exciting.
Yes.
Especially when you think about supernova remnants or some places in the galaxies that people have tried to characterize and where they see some elements that are difficult to be produced. Actually, strip stars like potassium, for example, gives very strong peak. That is a potential signature, actually, from binaries. So that's really exciting. So if we look maybe at some of the main structures that we see here, you can see that, so for the low proton numbers, these are really produced in a different phase, basically. So these are ejected mainly due to winds, and you can see that for both the single stars and the binaries.
Yes.
And for the high elements, it's kind of intuitive, right? You need very high explosion energies. You need high energies to produce and different processes to produce these higher proton number elements. So, but you can very nicely see it summarized here already.
Very cool.
Yeah, I mean, the one point I'd like anyone to take from this paper is that this is not a flat curve, right?
Yeah.
Depending on which elements you care about, you know, the contribution changes. So it's not a simple mapping between singles and binaries. You've really got to think about what the nucleosynthesis is going on and kind of how the material is getting ejected out of the star.
Yeah, and it turns out that it matters at which point this element is being ejected. And that's really the key difference between the single stars and the strip stars. Okay. So the reason why you have more of these low elements ejected, like carbon and these type of things, is that you actually have an exposed core, so you can see some of the products of like helium burning and beyond getting ejected through mainly winds, but also potentially Roche-Lobe overflow into the environment. And that's something that single stars can't do because they retain these huge hydrogen envelopes.
Yeah, they're on the inside even. Very cool. Very cool. These are lovely plots. Very nice. Congratulations. Good summary.
Thank you.
Good summary.
So yeah, we can start to kind of dig in a little bit into kind of where different things are coming. So if we go to figure 2.
Okay. Supernova evolution, composition of the winds. And here we go. Figure 2.
Yeah, so what we're showing here again, so again on the x-axis is the proton number. The y-axis is this kind of neutron excess.
Yes.
Kind of we picked this so that you can get a nice condensed plot mostly. What we're kind of showing, so what's in red is basically the difference between whether something is coming out of a stellar at the winds in a binary, or is it being ejected during Roche-Lobe overflow in the binary. So if you're red, you're basically being ejected during a wind. And if you're blue, you're being ejected during Roche-Lobe overflow.
Okay.
And the interesting thing to think about is that these are kind of 2 different phases. So the Roche-Lobe overflow happens while the star's still kind of got a hydrogen envelope.
Okay.
So it's quite early, you're crossing the Hertzsprung gap, this kind of phase. Whereas the winds for these stars, most of it's happening when you're into the core helium burning. And as Eva said, when you expose the core and you can get that out.
Very cool.
So the interesting thing to look at is that for one of these things is a carbon-13. So the kind of very dark blue point. Because this is one of these ones where it's really clear that the carbon-13 is ejected during Roche-Lobe overflow, while carbon-12 is ejected in the winds. So there's a very, very distinct phases of when these things are being ejected. And carbon-12 to carbon-13 is a ratio people can observe in stars. So
and carbon-13 I think is probably something to do with S process as well in massive stars. So when it comes out is interesting for that as well.
Yeah, but one of the things we discuss about in this paper, if we go to kind of table 1.
Table 1, few isotopes, table 1, here we go. Very nice. Okay.
Is that, so you can kind of see, so this is breaking down this ratio at different points in time. So you can see, from stellar winds, right, if you just look at the winds, if you could see a single star, right, that's 50, binary is 800. That's quite a big difference in this value. And one of the things to think about is, as carbon-13 is being ejected during Roche-Lobe overflow, does it, stay on the companion, right?
Yeah, right.
It gets we assume it gets secreted onto the companion, but the companion might process it, it might eject it back out. Right. So in principle, measuring this ratio of carbon-12 to 13 in a massive star region can give you some handle on kind of how much material this accretor is going to be spitting back out again. Does it reject the carbon-13 material? That's going to tell you, how much of the accreted material it's sending back out.
Yeah, and that's potentially a measure of the efficiency of this process, which is currently not very well constrained in binary evolution. So this has very nice potential. So any observer out here, pay attention. Sorry, pay attention to this ratio. It has really some potential here. It's very cool.
All right, we have a diagnostic.
Yeah.
Calling all observers. Very good. Cool. Okay, got it. I'm with you. Okay. Onwards. And you got them. You want to explode them?
Yeah.
Yeah.
So as Eva was saying earlier, there's different ways you can pick your explode. Which stars you think explode. Probably you'd have to do a 3D simulation to find this out. So we do a variety of fits instead to try and make some estimates of what the difference is. So what we're seeing here is on the x-axis is the initial mass of the stars. So in blue is the single and in the red is the binaries. And then on the y-axis is compactness parameter. And then the symbols are actually the second criteria we're using, the Ertl criteria. So
Okay.
where the stars are explosions, making neutron stars, and the black dots are we assume would make a black hole.
Got it. Okay.
And so you can immediately see that the landscape of explodability and which star is going to explode, which star is going to create a black hole, is shifted between the single stars and the binaries. And that's really a very important message in general. It has lots of consequences that basically the strip stars will not have the same outcome as the single stars, even if they were born with the same initial mass, and even if they have the same core mass. So both things are quite exciting. And as you can see, strip stars in general are more explodable. Like there are more regions where you will form neutron stars for the strip stars in general compared to the single stars. Yes, and this has a number of consequences also here for this paper, because you can imagine that if they're easier to explode, well, they can eject stuff around them more easily as well.
Nice plot. Okay. Very cool. I'm with you. Good. All righty.
So if we go to figure 5, we can kind of see the outcome. So so one of these, so we evolved these models, as said, in MESA up to core collapse. You can then basically cut out the core of the star and then inject some energy that you think is going to be your explosion energy. Watch the shock wave propagate through the star and do some nucleosynthesis. And then you can say, you know, what's coming out at the end.
Okay.
So what we're showing here is, so there's basically, it's the same data kind of in both plots. So on the left, again, the proton number for the different elements. And this is just showing you the absolute mass being ejected. In blue for the singles, red is the binaries. And then we've also got a couple of comparison, some other works. So we chose this mass. So this is for a single 13 solar mass single star or a binary star. We picked this one basically is the best one we could use to compare with other people's. So the left is kind of the absolute values, but if we focus on the right-hand plot, so in here we basically just divided out by the single star ejector, just to kind of, so we can kind of see the differences. So we can see kind of, so this red line is our binaries, so we can really see that the binary is making a huge amount more, say, potassium, right? This big peak in the center, than a single star would be. And then, you know, you see other things, you know, it falls down actually a little bit for the heavy metals.
That's an interesting potassium peak for sure. And there's, if I remember right, there's only one stable isotope of potassium. Is that right?
I think so. There's 40.
Okay, 40. Yeah, interesting. Okay.
And something else you can see from this plot, which I think is concerning, is that so we do see a very clear difference between the single and the binary models, but we also see clear differences between different calculations of different groups. And that is because there's a lot of physics and a lot of different assumptions that go in making such models. And so, unfortunately, there's no consensus yet. But it's still important to know. And I think this means we actually need to compare to observations to finally settle this. But the key point we still want to make here is that even though, yes, you could argue that there are quite large differences also with different groups for single stars, but there are really systematic differences between the single stars and the binaries regardless. So this difference between single and binaries is also something we need to think about, especially when it comes to production of elements like potassium that you just don't get in single stars.
Right. And remind me a bit, these other works were single stars, correct?
Yes.
Yes. Okay. Oh yeah, definitely a binary difference. Yikes.
Yeah.
Very cool. Okay. Nice.
Yeah.
All right.
And I mean, one of these things that, we kind of try to explore in this paper is what's the uncertainties on these values. And,
Yeah, and something that's really nice is that not only what are the uncertainties, but what are the uncertainties for which phase. So, for example, what are the uncertainties in what we assume for the explosion? And so we can show you that in the next plots.
We go to 5 or
that's figure 7.
Figure 7. Let's go to figure 7. Ratio of variations. Okay, let's see.
So what we're kind of shown in the color bar here is kind of a measure of how much, things change if you change your explosion physics.
Okay.
So for a single mass model, we basically randomly picked the different explosion parameters.
Okay.
To kind of explore what is the range of values you could get.
I'm with you.
And then this delta progenitor is kind of what's the difference, what's the biggest spread between kind of the lowest ejector from one of the stars and the highest ejector.
Okay.
So it's a measure, if you didn't know what star you were looking at that exploded, what's the possible differences there versus so if you're in blue, so you're very small value, basically you are it's telling you, let's get this right way around. So this is telling you when the delta explosion is small, so this is kind of progenitor uncertainties. Cool. And then when you read, this is the explosion uncertainties.
Dominated, right. So which phase is dominating the uncertainties? Yeah.
And the key, I mean, there's a lot of, details in the individual color blocks, but really, if you just qualitatively left to right, it's different again. Yeah. Right. Binaries and the single stars are uncertain to different physics from different bits of the evolution or the explosion, which means, if there is a difference, that means you can use that difference, potentially to start to probe the physics there. If you see binaries or if you see single stars, you can start to look at how these things are varying and perhaps then get a handle on some of these uncertainties that we have in the models.
Very cool.
So I think that's really the value of this paper, that we're not only trying to say, oh, it's different for strip stars, but also where is it different? And what can you look at to try to reduce the uncertainties that we have?
Very nice. Cool. Very good. Okay, so that's figure 7. And that's the talk about the uncertainties. We talk about a few gamma ray emitters.
Yeah, so this was just there's a paper a few years ago by Andrews, 2020, that was looking at kind of what the next generation gamma ray detectors might, want to focus on.
Right.
And, it's a combination of what isotopes have interesting lines that you could see, and also would be produced inside a star. And again, we're coming out with this thing that basically the singles and binaries are sensitive to different isotopes. So again, potentially that's giving you some information if you could find them, that would be telling you something different between these objects.
Very good.
And it's also important to remember that also between the single stars and the binaries, what kind of isotope you will observe will probe something different. Like we can probe the explosion physics, or it can be more sensitive to what kind of progenitor you have. So it's also important to look at these differences, and that's why we try to characterize this.
Very nice. Very good. Very cool. And aluminum-26, of course, is a special one. Anna Brinkman's been doing a bunch of stuff on that. Very good.
So I think if we go to table 2, so that one of the main things of this work is that we've put these tables online on Zenodo. So all the data that you want is available in table form. All the model information is there as well. If you wanted to make your own runs based on this work, you can do this. So what table 2 is shown is just a kind of representative of the data we've got. So this is just fluorine 19. Just pick that because it's kind of interesting. And you can start to see that, we can break down the mass of the material coming out from the different mass loss processes, the winds, core collapse, Roche lobe overflow. And also, importantly, we're also including the initial values for these things. So if you want to know the yield, the net outcome, you need to know the initial amount.
Very cool. So those of you who are people out there interested in chemical evolution, this is an outstanding set of data sets to put in and do some binary chemical evolution for all the isotopes.
Exactly. Or compared to observations.
Or compared to observations, absolutely, on particular ones. So, so these are really awesome appendices. So we got data tables, and again, this is just a small fraction of the whole thing. We have the sensitivity to the wind, right? Because you got to pick a wind. Some of the uncertainties there. The evolution properties are in Appendix D, and Appendix C, I think, is the explosion properties. Yes. Yeah. There's a rich data set here to mine, people.
Exactly.
Yeah. So we have these tables structured. We've also got the MESA output, so that's got a lot more information in there as well.
Okay.
But, quantities that we didn't put in a table, you could find if you wanted.
Okay. Yeah, and because these models took like months to run, this is precious output, so lots of people can make use of it without having to burn more resources to create this.
Absolutely. Very good. Very good. And we got some summary stuff. You want to sort of summarize it all up?
Yeah. Sure. So the big summary really is that we really got to think about binaries being different to single stars.
Yes.
This is really the main point that we want to hammer across to people, that it's not a trivial function to map between binaries and single stars. It really depends what you want to look at.
Right.
With the differences.
It's not just an addition.
Yeah.
Very cool. And we got a tag there, 12-13, carbon 13 to carbon 12 ratio. Check that out. And lots of differences in the abundances. Very cool. Very nice. Well, Rob, Eva, thank you very much for walking us through this very awesome article on really the first study of nucleosynthesis in binary strip stars. Way to go.
Thank you.
Yeah, thank you for the opportunity.
Sure. And you mentioned a little bit as we went through. So let me push on it a little bit. So where do you think we go with this, let's say, over the next 2 to 5 years? Are there additional models to be run? Might some of these be picked up, even by 3D core collapse types? Are there observations? You mentioned a couple that can help decide whether we're doing single or binary. And so just sort of in general, where do you think we go with this topic over the next 2 to 5 years?
Yeah, so I think certainly there's a lot more models. So binaries, find very interesting, but unfortunately, if you add binaries, you expand your parameter space, right? So now you've got to pick the masses, you've got to pick a period, possibly an eccentricity,
and
this gets a lot,
possibly
kind of explodes what you have to do.
Yeah, and the companion, like we only looked at one of the elements in a binary so far, right? So you got to also think about the accretor, and you got to think about things like mergers, and I mean that's a lot of work.
Yeah, so expanding parameter space, also to do kind of the chemical enrichment. We've only done one metallicity at this point, so it'd be interesting to go forwards to do more metallicities. What the differences are, because there are differences then in how much you get from the winds. The mass transfer also changes as you change the metallicity. So, there's a complicated feedback going on.
And some of that would be pretty interesting with, JWST and Hubble finding very early stars apparently at high redshift. So
exactly.
Very relevant. Very cool. Very nice. Well, great. Rob, Eva, thank you so much for walking us through your very lovely article.
Thank you.
Thank you.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. We will see you on the next one. Bye-bye.
Bye.